Now that we have gotten down the basics of using logarithms to solve equations, we're going to go ahead and look at some specific application problems where we can use logarithms to solve those equations. So let's remember back from chapter 7, we talked about compound interest, and particularly we talked about our general compound interest formula. Well, this was specifically our yearly compound interest formula. So this was the formula that we learned then, our yearly compound interest formula, where we know the amount, A, that's in the account after a certain amount of time has passed, is equal to P, the principal amount that we started with, the original amount, sometimes you might see it as A0, times 1 plus the growth rate as a percentage or as a decimal, and then that multiplier there is raised to T, the T power, where T is the number of years. For an interest formula, it could be a different unit of time depending on the situation. So in chapter 7, we used these formulas to determine how much there would be in an account if we knew how long it was in the account. So if we knew time, we figured out the amount. In this chapter, logarithms are the inverse of exponential functions, so we're going to switch that around. In this chapter, if we know the amount, if we know the certain amount that we want to be in the account, then we can determine the amount of time. So we're going to solve for t, figure out the time, right? Solve for t, since that's the variable in the exponent. And that's what we were using logarithms for the other day, is to solve when there's a variable in the exponent. So let's go ahead and get right to some examples. In this first example, we're just reminding ourselves how we use the formula. So this is actually much like a chapter 7 problem. It says if $500 is invested at 6%, how much will be in the account after 10 years? How much is chapter 7. That's when we're just plugging it in and evaluating the function. So we know that the principal amount we started with was $500. The amount of time that it's going to be in the account is 10 years. And the growth rate is 6% as a decimal 0.06. So the amount of money that's in the account will be equal to whatever we started with times 1 plus the growth rate raised to the t power, right? P times 1 plus r to the t power. So r is 0.06, t is 10, p, the principal, is 500. In this, we can figure out how much will be in the account after 10 years by just using our calculator here and plugging this in. We would have 500 times 1 plus 0.06. You can just type in 1.06 if you want, raised to the 10th power. And we'll have $895.42. Right, so there's a nice basic application, just like we would have done in chapter 7. We didn't use any logarithms. That's just reviewing how the formula works. Now let's go ahead and use our logarithms here and go with this question a different way here. It says now, how long will it take for the original amount, the original investment, to double? So here the question is changed from how much will we have, which is a straightforward plug it in, to how long will it take, which means our unknown is going to be this variable t. We're going to have to use logarithms to solve it. So what we want now is we want to figure out, so here, up here, a was the unknown, but we still have all basically the same variables here. But now we're going to know, we know a because we want to know when the investment has doubled. So the investment will double. That means there will be $1,000, right? That's what it would mean for the investment to be doubled. The principal, we still started with the $500, but now time is the unknown, and our interest rate is also still 6%. So we're looking at a very similar setup, but we've swapped two of the variables here. We know the amount that we want in the account, but we don't know the time. So now we can plug this in to our formula here, and we'd see that we want 1,000 is equal to 500, our principal, times 1 plus 0.06 again, same growth rate, but now t is the unknown variable here. So if we're going to solve for t, we're going to use our normal inverse operations. Divide by 500, and we have 2. And this is a pattern that you notice if you ever want to figure out how long it takes for something to double, you can just skip right to this part and say 2 is equal to the rest of the multiplier here. So anyhow, we'd have 1.06 raised to the t power, and this is exactly the type of equation we just got done practicing with in the first half of this section, where we can use logarithms to solve for t here. And so we can use any base we want. I've said that I'm going to lean toward using the natural log, and we'll see especially why I do that later on in this section, in this set of exercises we're about to do. But here I get the natural log is equal to of 2 is equal to natural log of 1.06 to the t power, right? And so what's nice here is that because it's inside a logarithm, I can move that t out front. And that will give me natural log of 2 equals t times natural log of 1.06. If I want to solve for t, all I need to do is divide by natural log of 1.06. And now I know what t is. T is exactly equal to the natural log of 2 divided by the natural log of 1.06. It might be tempting to try to combine things here using the quotient rule. We can't use the quotient rule. The quotient rule applies for when we're dividing two things inside of one logarithm, not when we're dividing two separate logarithms. But anyhow, here's our exact answer. And if we want to get a decimal approximation, which is probably more meaningful than this number when we look at it, we can just go ahead and divide that in the calculator. We want the natural log of 2 in the numerator divided by the natural log of 1.06. And we get, oh my goodness, we get 11.896 or 11.9 if we round. So this is 11.9. And so if we think about this, what is that telling us? This was t, the amount of time that it will take for our account to double. And this was measured in years, we saw. So this means it will take just shy of 12 years for our investment to double. Okay? And there we go. And that makes sense. After 10 years, it had gone to 900. Just a couple more years and it will be up to 1,000 and we'll have doubled our amount. So now let's see what would happen if we wanted to figure out how long will it take for the account to triple. It might be tempting to say, well, it took 12 years to gain $500. Will it take 12 years to gain the next $500, right? To triple would mean we want to get up to $1,500, still starting from 500, and we don't know how long that's going to take. That's our unknown. But we do know the interest rate is 6%. So it took 12 years to gain the first $500, additional $500. Will it take another 12 years to get to the next 500? And it may or may not be obvious that the answer will be no. So let's go in and see what happens here. We want to use our account or our interest formula here. It's A equals P times 1 plus R to the T power. So we know we want to end up with 1,500, and we started with 500. And we have an interest rate of 6%, right? And once we do this first step here, we know we got to divide that 500 out. And we see real quick, I have 3 equals 1.06t, and we're seeing how similar this is going to be to the previous problem. And in fact, we notice in order to double the account, I needed to take the natural log of 2, and now in order to triple the account, I'm just going to take the natural log of 3. So I want to take the natural log of both sides. And again, you can use any log you want. You can use common log. That's totally fine, right? And what that allows us to do now is bring this t out front, right? So we'll have the natural log of 3 equals t slides out front of the natural log of 1.06. and we come to the same basic format of our answer here. We divide by the natural log of 1.06. Same process as previous problem. And we end up with our value for t is the natural log of 3 divided by the natural log of 1.06. And you could see real quick, if I wanted to figure out, well, in order to double, I did natural log of 2 divided by natural log of 1.06. If I wanted to triple, it was a natural log of 3. If I wanted to multiply it 10 times what I started with, I would just have natural log of 10 here. So we could keep growing it really quickly without having to work through all of those all of those steps if we wanted to. And to see what this is as in a number that makes a little more sense to our eyes, we'll just go ahead and bring down the previous expression, but change that 2 to a 3, and we see 18.85 or 18.9 years. So it'll take just shy of 19 years for our account to triple. So we saw that it took about 12 years for the account to grow by $500. But once I've already done that once, it only took me about another 7 years for the account to grow for the next $500. And this is exactly what exponential growth means and is or sometimes we'll call it proportional growth, is it takes less and less time to grow by the same amount versus a linear function where it takes the same amount of time to grow by the same amount and it's constantly taking the exact same amount of time to grow by the same amount. That's a linear growth function. An exponential growth function is exactly what we're seeing here. We'll grow by $500 in 12 years, but then it will only take us 7 years to get the next 500, and it will only take us another 5 years to get the next 500, and it'll be a shorter and shorter amount of time to grow by $500 each time we do it. Okay. In the next few examples, we're going to look at the continuous growth function and see some specific examples of how we can apply logarithms with continuous growth.